d over dt, d over dt, Let's go.
Sketch, you tell him.
Hey, just a reminder, position is given by x of t and y of t. Velocity in the form dx over dt, dy over dt. Acceleration in the form of that double dx over d double t. Part 2, we got double dy over d double t. Hey, dy dt, grow like a tree. Dx dt, flat as a v. Dy dt is vertical, dx horizontal, that is the key. The motion is in 2D, 2 dimensions, won't you agree? Root of each of the velocity functions squared, that be the speed. Hey, let's talk about dy dx, that's the topic up next. It's a little complex, think velocity functions having dy dt on top, dx on the bottom, they never ever swap. That's how you can calculate the 2D slope of all of the ops. A position vector is x of t, y of t. Want the velocity vector, take each function, d over dt. Want the acceleration vector, do it again, d over dt. Wanna go backwards, you can do it, I can guarantee. Haha. Hey, one more thing. Remember that speed function, the square root of dx dt squared plus dy dt squared? If you want the total distance from one time t to another, you can integrate that speed function with the 2 times as the bounds. Hey, just a reminder, position is given by x of t and y of t. Velocity in the form dx over dt, dy over dt. Acceleration in the form of that double dx over d double t. Part 2, we got double dy over d double t. Hey, dy dt, grow like a tree. Dx dt, flat as a v. Dy dt is vertical, dx horizontal, that is the key. The motion is in 2D, 2 dimensions, won't you agree? Root of each of the velocity functions squared, that be the speed.
For the first problem, we need to find the position of the particle. From the graph, we can tell that the y position is going to be negative 1/2. We aren't given the x position function, but we are given the x velocity, so we can integrate it to get the change in position from time 0 to time 3, and then we can add it to the initial position. So when we integrate it, we're going to get this formula, then we're going to add the initial position, which is 5, and we're going to get 14.377. So our position is going to be 14.377 and negative 1/2. Now for the second part of the problem, we can remember that the slope is dy dx. So for dy of dt, we can use the graph, and at t equals 3, we find that it is 1/2. For dx dt, we can plug 3 for t into the equation that we're given, and we would get 9.956. And then we can plug in our values into the original formula we're given of dy dx. And we would do 1/2 divided by 9.956, and that would get us 0.050 as our slope. For the third part of the problem, we know that the formula for speed is the square root of dx dt squared plus the square of dy dt. And so we can just plug it in for 3 for both of dx dt and dy dt. So that's going to become square root of 9.956 squared plus 0.5 squared, and we're going to get for our speed 9.969. For the fourth part of the problem, we need to find the total distance. And the distance is just when you have to just integrate the speed. You just have to find the total change in speed, right? So we can, since we know that we have to go from 0 to 2, we can integrate from 0 to 2 the speed, which was dx dt squared plus dy dt squared. However, we realized that dy dt isn't written in an equation. We don't have an equation for y of y of t. So dy dt we have to get from the graph, but we can just make that into two integrals. So the first integral goes from 0 to 1, and that's the square root. This is the square root of dx dt squared plus dy dt squared, with dy dt in this situation is just going to be -2. So we plug that in here, and then we're going to add it to the integral from 1. We're going to add it from 1. We're going to from 1 to 2, and that one, the slope of y is 0, so it's just going to be dx dt squared, and we're going to plug that into our calculator, and we get 2.238 plus 2.112, which is going to be 4.350 units for the distance traveled by our particle.